this computer. Okay, so here we have Rolando to speak about L2 cohomology and maximal rigid subalgebras from Purdue University. Thank you very much for accepting the invitation, and well, you have the floor.
Thank you very much for inviting me. This is, I think, my first post-COVID talk. So I really want to get a feel for giving a talk in this setting. So thank you for allowing me that. What I'm going to discuss right now is a work that, some results contained within the work done by myself, Ben Hayes, Dan Hoff, and Thomas Sinclair, where we discuss some of the interesting structures that you can find in von Neumann algebras, at least through the lens of deformation rigidity theory. There's a lot to define here. So my plan is to start off by going through, the basic setup. After that, I'll go through some background on deformation rigidity. I will also present the results that we have. Rather than to focus too much on the proofs that we have, I want to focus more on like the motivation for like just the statements of the results. And then I'm going to close off with some further directions that I think are, some interesting problems that we think we could tackle using this method. So with that in mind, let's get started. So the setup that we're going to be working in is the following. We're going to start with, whenever I write the symbol H, this will represent some sort of Hilbert space. Usually it's going to be a separable Hilbert space, unless it's not. B of H, this will be the bounded operators on that Hilbert space. And then whenever I have a subset of the bounded operators on this Hilbert space, I will write this prime symbol to denote the set of all elements in B of H with the property that they commute with every element in the initial set S. By the way, I should mention that sometimes my internet is unstable. I've had a problem with that in recent days, so please bear with me. There will be lag. There will also be a lot of noises coming from the main street. I apologize, but there's nothing I can do about traffic. I've tried.
Don't worry.
All right, so this, in words, this is the commutant of Now, what I'm really going to care about are very special subalgebras of B of H. So those are so special, they're going to get various letters. So P, Q, M, maybe N. These will all denote von Neumann subalgebras of B of H. And what are these? These will be unital, i.e. they contain the identity is in, this way, contain the identity operator. They will be algebras. Closed under addition and multiplication. But writing on this surface is a little odd. Both by scalars and by, in this case, the multiplication operation is composition. And they will be star subalgebras, meaning that if, let's say, X is in, for instance, M, its adjoint is also in M. And finally, the real defining feature of all this is that these algebras are closed in the strong operator topology or the weak operator topology. So let's just write, I'll choose the weak operator topology. So closed in the weak operator topology, which is already abbreviated, but I'm going to abbreviate it slightly more. WOT. What does this mean? Well, the idea is that if you have a sequence, or more generally a net, in this star subalgebra, and you also know that there exists some bounded operator out there with the property that if when you look at this new sequence of this new net, here this is the inner product on H, and here these are arbitrary pairs of vectors in this Hilbert space in which you're acting. This should not equal 0, but this converges to 0. Then it better be the case that X is also back in this algebra. So this is the closure property that we want. Okay, so informally what this should tell you is that if you have an operator out there whose matrix coefficients can be approximated by operators in M, then that operator that you're approximating better be inside of the algebra in the first place. And so sometimes I'll just say, I'll write it like this. M is the same thing as M closure with respect to the weak operator topology. So it's a pretty loose form of convergence. And you can imagine that this is going to introduce a lot more operators and say, let's closing this in the uniform topology. So these things are going to be rather large monsters that you're going to be trying to understand. Okay, so all this is you know, all this is mysterious. It's nice to have some examples, but before we get into examples, I need to mention one last property. The reason why I introduced this commuton condition is the following theorem of Murray and von Neumann. Which is that M is a von Neumann algebra. If and only if M is its own bicommutator. I'm being a little loose with what's going on here. There's some other conditions, but this is what you really need to know. It's an algebra of operators that's somehow perfectly balanced with respect to this commutation condition. Okay, here, if I wanted to be a bit more precise, I would say that M is a unital star subset, and if it's a star subalgebra if and only if this property holds here. So just let's go back. This is an observation. For any set S, you always have this inclusion. So a von Neumann algebra is an object where you have an equality here. There are many examples. The one that I'm going to focus on, star of the show, ooh, the capitalization is all over the place. the group von Neumann algebra. So what is this object? Well, it's built this way. First, I'm going to start with a group G, which will always be a discrete, countable group. Since this is a discrete countable group, I can build a separable Hilbert space out of that. And for now, we'll focus on our attention on L2 of gamma. Oh, sorry, old habits. L2 of G, i.e. the square summable sequences. Indexed by G. And now I need to define some operators. To do that, I'm going to use the left regular representation. So just for notation, we're going to let delta G, these will be the canonical basis vectors. And in order to assign an operator, for historical reasons is always denoted by lambda, I'm going to use the following formula. This operator, lambda of G, acts on a canonical basis vector by sending this basis vector to this new basis vector, delta GH. So in particular, it just shifts the basis vectors using the multiplication on the left. And so this will in fact be, so this defines a collection of unitary operators. And moreover, it's a faithful representation of our initial group, meaning that we have some sort of preservation of the group operation. So if you have lambda G1, G2, that's the same thing as lambda G1 goes multiplied by lambda G2. And in fact, the adjoint, since this is a unitary, you can check that the adjoint here corresponds to the inverse group element. So let's zoom out slightly. So now that you have these collection of unitaries, we can build an algebra out of them. We can consider either the group ring inside of the bounded operators on this L2 space. You can take that, close that in the weak operator topology. Here, I'm constructing the group ring by viewing, by looking at, sums of these unitaries, right? You have building linear combinations here. this is by definition the group von Neumann algebra. Go away. This is the group von Neumann algebra associated to the group G. So you start with the left regular representation, build an algebra, close that up into topology and the weak operator topology, and there you go. You have an example of a von Neumann algebra. And what's nice is that L of G is a tracial von Neumann algebra. What this means is that there exists a function going from L of G into the complex numbers, which is a state, meaning that it's linear since 1 to 1. It is positive, means it's that you start with a positive operator. The output will also be positive. It's faithful. If you have equality in the line above, then that necessarily implies that you were starting off with the 0 operator. And it's normal, which is essentially just means that it satisfies the monotone convergence theorem. If you have an increasing sequence of bounded operators, if you have a bounded increasing sequence of operators, you get continuity like so, whenever these things are bounded and increasing. So I'm not going to dwell too much on that, because the real important part here is the tracial part. This state satisfies the following property. Tau of xy is the same as tau of yx for every x and y in L of gamma, L of G. Sorry. And much of the results that I'm going to present apply to more, not just necessarily group von Neumann algebras, more generally, they apply to tracial von Neumann algebras. A reoccurring theme in the study of, at least in the work that I study, is the recurring theme of the problems that I study is something like this. You study a phenomenon for group von Neumann algebras, and then ask whether this is something that's intrinsic to the group structure, or whether or not this is some sort of general phenomenon that occurs for all von Neumann algebras. And that is one direction that you can take. I could spend an entire class on just that philosophy. Not necessarily what we're going to focus on right now, but know that's sort of what's motivating a huge amount of the problems that we're going to be that people in my area look at. Okay, but before I get into that huge problem, let's start with a seemingly simple question. How much of G does L of G remember? Are there structural aspects of this group that are somehow still recoverable from the group von Neumann algebra? How can we use those to build invariants? You know, a seeming, and let's start very simple. Is it possible for you to build two potentially different von Neumann algebras? Let's say you started with a group over here. You built its group von Neumann algebra. You know there's another group von Neumann algebra out there that's isomorphic to the thing that you've just built. Does that imply that G has to necessarily be isomorphic to H? Right, that's in the vein of what we're discussing here. If this is possible, if G is a group, which satisfies this kind of condition, G is a W star super rigid group. Okay, so if you know that you necessarily have to have an isomorphism of the groups, that's what W star super rigidity is. That seems to be like a very rare phenomenon. In fact, some of the first examples of such groups weren't uncovered until I'm blanking on the exact dates. It's either 2011 or 2009 by Joanna, Popa, and Voss. So these kinds of results are really hard to come by. So let me just write that down. Joanna, Popa, and Voss prove such groups exist. In, I want to say 09. I'm going to put a question mark there. And this was proven using Popa's deformation rigidity theory. This is a term that's going to come up a lot. I'll describe more about what the framework is for Popa's deformation rigidity theory a little bit later. But it is a powerful way to try to unravel some of the underlying structure of the group von Neumann algebra. Use it by trying to import certain aspects of the group into this setting of analysis. Again, how much of the group does the group von Neumann algebra remember? This is like the main motivating question. So first, I want to present a result proved by me and my collaborators. And I sort of want to peel this result backwards. I'm going to give you the results, talk a little bit about the motivation, talk about the proof of the motivation, and then just claim that there's a parallel analogous result that holds for this analytic setting. And that doesn't mean much right now, but bear with me as we talk through this. What we are able to show is the following. If you have two von Neumann subalgebras of the group von Neumann algebra LF2, and you know that their intersection is diffuse, which for now we'll just take it to mean large. Maybe even stronger than that. Let's take it to mean large enough. And P, these two Neumann algebras have property T. Which we'll take to mean some sort of trivialization, which we'll unpack a little bit later. Then the von Neumann algebra generated by both is a strict von Neumann subalgebra of LF2. And without motivation, this sort of result doesn't, I think that there are a couple questions that stand out here. The first question that I have, if I'm just presented with this result, is what? The next thing that I might want to ask is, huh? And more importantly, why? Why would someone even conjecture a statement like this to hold in the first place? And finally, I would also like to know who cares? Right, these are all important questions in every aspect of research. How do I clarify this result? How can I make it even more clear? Why is it important? And to whom? So let's start off with a little bit of motivation from groups. If I start with a countable group G, I can describe a function, C of G going into L2 of G. Why are you treating me like this? Okay, so it's a function that takes in elements of the group and spits out vectors in L2, and it has the following properties. Well, C of G, H should be C of G plus C of H. So at the moment, it looks just like a homomorphism, going from the group G into this additive group L2 of G, but I'm going to give it a twist. I'm going to take this left regular representation and apply it to this second component. C is a 1 cocycle or an L2 cocycle. And some of the nice examples, these are abundant. These are easy to construct. And in fact, the easiest way to construct them are in the following way. You just define C of G to be, well, you take your favorite vector inside of L2, and just compute this thing. And you can check that this formula defines a function with the property here. Notice that there's this fixed vector here. So cocycles of this form are termed inner cocycles. So in some ways, these are our trivial cocycles. And earlier we talked about property D sort of being this trivialization. That's going to show up in a minute. A little bit more about cohomology for groups. We define the first L2 Betty number of a group. This is the dimension, though I have to be a little bit more, I'm going to sweep the details of how you compute this dimension under the rug for now. This is the dimension of the space of all cocycles for G modded out by all inner cocycles.
Sorry, can I just ask a quick question?
Yeah, please.
This number 1 in cocycle, what does it refer to?
This number 1 up here?
Cycle.
Is that the one you're referring to?
No, this is a 1 cocycle. I'm just wondering why 1 or 2 or 3 or...
Just like with just general cocycles, you do for, from topology, there are these levels of cohomologies that you build. There is something in here hiding under the rug, right there. There are higher cohomology classes here that I could be describing, and I'm not necessarily going to do that.
Okay, thanks.
Mainly because it's not fresh in my mind.
No, okay. No, go. Thanks.
Yeah, there's a deeper theory of cohomology coming in here. So yeah, this one up here that I'm pointing to reflects the fact that we're just dealing with this sort of first cohomology class.
Thank you.
There is something called the bar resolution. Again, just I know I'm going to get it wrong for now. Okay, so this is what it is, and then maybe it's nice to have some examples. You can compute these in some cases. You take the free group on n generators with n at least 2. This dimension boils down to the number of generators off by 1. Why is this important? Well, it turns out that if your group is non-amenable, more undefined terms, but for now, just Fn with n at least 2, and in fact, various hyperbolic groups are important examples of non-amenable groups. If you have a non-amenable group and you compute this number, then what you know is that there exists some cocycle which is unbounded. And in particular, it is definitely not inner on this group. It's not implemented by a single vector using this kind of formula described above up here, right? So there's some non-triviality going on when you're dealing with a group of this type with positive L2 Betty number. So let me write a statement So now that we have this sort of terminology, here's a fact. If G is a group, again, you're more than you can hold on to the free group. You can take certain free products of various groups. I'm going to brush that aside for now. If G is a non-amenable group, and you know that its first L2 Betty number is positive, then for any pair H1, H2, subgroups of G with property T and with large intersection, we must have that the group you generate using these two subgroups is a strict subgroup of G. The way this works is by using this sort of cohomological data, referring back to this sort of trivialization phenomenon, and just making sense of all this. So how does this all work? Well, let's start with the fact that this setup now shows that the first L2 Betty number of a group being positive implies the existence of a cocycle, which is unbounded and hence non-inner, meaning not implemented by a fixed vector across the whole group. But since H1 has property T, we have a trivialization going on. So if you take this same function, but you restrict to H1, this is inner on just this subgroup. And I can do this for H1 and H2, so I'm just going to write HI here. And since these are inner, C restricted to HI of H is given by some fixed vector and so we have this formula for every H in HI. Okay, so it's inner, not on the whole group, just on this small chunk. Rearranging this, you know that if you focus on the intersection, you get the following formula. Lambda of H on XC1 minus XC2. This vector will be fixed by every H in this intersection. And since we're using the left regular representation, which does nothing but shift the indices, right? This can't happen unless this vector right here, this difference, was necessarily zero, right? This is where the condition that this being infinite has to show up, right? Infinitely many coefficients have to stay fixed somehow. That's just not necessarily possible here. So it has to be the case that this has to be, these two vectors have to be, sorry, this difference has to be 0, so these vectors have to be equal. And what that means is that we can essentially patch this cocycle from not just one group to the other, but across their intersection into the group that they generate altogether. Okay, so in fact, which I'm just going to denote by C naught. C restricted to the group generated by H1 and H2 always looks like C0 minus lambda of H over on C0. So what you're saying is that it's necessarily inner on the group generated by both H1 and H2. And H1 and H2 can't be the group you started with. It has to be a strict subgroup. And what's nice is that this is, this is something that, if you sat down for about half an hour, you could figure this out for yourself, and it's kind of nice. The proof is easy to write down. The statements are, for someone who's a little bit more eloquent than I am, it's very easy to explain to somebody, even a student, right? I like the proof. How can I take these results and lift it up to the level of the von Neumann algebras, right? What are the appropriate modifications that I need to make? And how can I copy this proof? Because I like it so much. How can I take this exact same sequence of statements and apply it to the group von Neumann algebra and get something similar for property T subalgebras instead of property T subgroups with large intersections? Okay, so another question. How do we take this result and apply it to the level of the group von Neumann algebra? One answer to this is Popa's deformation rigidity theory. So Popa's deformation rigidity theory is this whole framework that allows you to import various pieces of cohomological data into this whole language of von Neumann algebras. And the subtlety about this is that it's really an art, right? There, you have to somehow take things on a case-by-case basis, see if you can somehow build what we call an s-malleable deformation out of it, and use that to extract certain structural properties of the von Neumann algebra. So how does this, what is this framework? How does it all behave? Here's our general setup for Popa's deformation rigidity theory. We're starting with a von Neumann algebra. And here's where the art comes in. There's a larger supra-algebra that you're going to be working in, which I call M tilde. But I'm going to put a question mark because it's not really, there's no like prescribed way to get at this larger subalgebra to always get some unique results, right? As I mentioned, it's a case-by-case kind of thing. And what you do is you should have an action of the isometries of the real line. What that means is you have a couple of things. You have a one parameter group, alpha t, automorphisms of this larger algebra, a one parameter group. you have this beta, just a distinguished automorphism here, which fixes this underlying algebra that you're really trying to understand, M. And it's compatible with this alpha t in the following way. Alpha t beta, beta, alpha t. What you're really doing here is you're having like this sort of flow, this stochastic, this sort of like time reversible stochastic process occurring inside of this larger ambient von Neumann algebra M. You're allowing it to flow. You also want alpha t to converge to the identity on M tilde pointwise. And this whole framework here that I have, this whole setup that I have up here, this is what this pair M tilde alpha t and this beta is an s-malleable nation of M. Go to a larger space, allow it to flow and deform. So at least there, that's the name I think is, at least to me, it makes sense. So there's a deformation. The S is for the symmetry across time, right? You have alpha, oh, I made a mistake here. There's a time reversible process portion of this. And then finally, let's see what, so that's all I have here. Yeah. So what are some examples? I can't be too explicit given the amount of time that I have left. So I'm just gonna give you an example created by Adrian Joanna. To study these von Neumann algebras coming through these free groups. You're looking at, let's say, LF2 inside of the von Neumann algebra generated by the free product on two generators. Well, this is the free group on four generators, but I'm distinguishing up these generators by splitting up into pairs in a particular way. And there's Joanna was able to describe a deformation that allowed you to sort of carry this F2 in let's say like the first part onto the second part. And so there's a way to use this free deformation to flow these generators over here to the generators on the other side. Okay. Thomas Sinclair gave us a different deformation, and this one is one that's coming from cocycles. What Thomas Sinclair was able to do was to show that if you have a group and you have a cocycle, doesn't necessarily have to be bounded or unbounded, but just as long as you have a cocycle, there you can construct an action of a group on some measure space such that, let's say L of gamma inside of L infinity of the space crossed by gamma. There's a larger von Neumann algebra out there. This is your M inside of your M tilde. And you can, in fact, use this cocycle, can be exponentiated to produce this sequence of one parameter groups. And so this one parameter group of automorphisms and this like flip automorphism. There's a pretty canonical way to do this. And this setup, like I said, it's really an art. So we take this setup described by Thomas Sinclair, and we apply that to, and we use this framework to actually use almost exactly the same proof, just with, instead of having equality everywhere, we have a few more estimates. And that's how we are able to make the conclusion that I presented earlier using T. Sinclair's deformation, which is known as a Gaussian deformation. We can conclude that, you know, if you have P and Q inside of LF2 with property T, and large intersection, then it has to be the case that P and Q can't generate this Neumann algebra for basically the exact same reasons. We copy the same proof, and that is, in essence, the power of Popa's deformation rigidity theory. I can take exactly what I wrote on one page, copy it over into this land. There's, in fact, a lot more that we can say. I didn't go through the rigidity aspects of deformation rigidity. Just know that rigidity takes this pointwise convergence that I described here, I upgrade that to uniform convergence. And property T is precisely that sort of like trivialization, right? It takes this weak condition of pointwise convergence and upgrades it to a much stronger condition like uniform convergence in some sense.
Question?
Yeah.
Is that convergence as T goes to 0?
Yeah, did I think in my head, yes.
Oh, okay.
I think in my head I said it, and that's
Yeah,
where a lot of things tend to stay.
Thank you.
So I upgraded to uniform convergence to the identity in some sense. I'm not going to get too much into that, but that's property T subalgebras satisfy this kind of phenomenon. They are, you try to deform them, but whenever you do have this uniform convergence back to the identity when you focus on that subalgebra. Since the idea behind the proof then is if you take these two property T subalgebras and you join them, their join is also shares this kind of nice uniform convergence to the identity on this thing that they generate, so you can patch it through just like you would in the group case. Okay, so I'm not able to say too much else, but I am going to mention some of the other questions that I'm investigating in this sort of scheme. So here's a fact. If that's a G is a property T group, then anytime you try to construct an s-malleable deformation, is necessarily giving you uniform convergence. in the setting that sort of the setup that I had above. All right. What I'd like to study is this. Let's say you take a sequence of groups, G1, G2, all the way up to G, which increase up to G, each of which property T. A nice a fact of these LFGIs is that these have what's called at most countable fundamental group. What this fundamental group is this I don't know if I have time to describe it too clearly, but it is these collections of projections inside of this algebra, which you by taking their trace do form a subgroup of the real line. The question that I'd like to ask is, does it necessarily follow that L of G has at most a countable fundamental group? In my title, I included something about maximal rigid subalgebras. And by going, I wish I had a bit more time, but I do need to get off of this space because shared workspace. I'll answer questions in a second. The idea is that if you have these sorts of increasing things of rigid objects, the resulting object is rigid. So I have this increasing, here I can consider this increasing chain of rigid group von Neumann algebras, which increase up to this larger object. And I'd like to say, you know, in what ways can I approximate the properties of this larger group up here by using these smaller, sort of like these building blocks that slowly approximate it. And I said that there is some evidence to show that such results can probably be obtained by using the results of Ben Hayes, Thomas Sinclair, Dan Hoff, and myself. This, along with the fact that there is a shocking amount of evidence that property T groups arising from various constructions have like trivial fundamental groups in many cases. Like there's these really nice natural ways to build examples of groups like this from like a single extension of property T groups. And I'd like to know whether or not, you know, we can take this to the limit essentially. That is all the time I have. I will take questions, but I need 2 minutes to move to another space. I apologize.
Thank you. Thank you for the talk.
How's everybody doing?
Good, all good.
Good.
Locked at home.
So Rolando has his cat there in that photograph. I should call my 2 dogs back. They were up here on the bed a while.
What kind of dogs do you have?
Hmm?
What kind of dogs do you have?
I have 2 Bichon Frises.
Oh, oof, wow. Okay.
I guess Rolando's back.
Ronaldo's back. We can take questions now.
Hey, Rolando, thanks for the talk. So yeah, questions, I guess.
I apologize for
No, don't worry. Are there any questions to Rolando?
So I guess I have one. So this countable fundamental group question seems really interesting. It seems likely that yeah, maybe from the group level you can do it for these like inductive limits of property T groups. Like, I guess it's not a well-defined question. I'm just sort of wondering, like, how much of this can be pushed through. Like, if you just assume that you have a group for which like it's rigid with respect to every deformation coming from like the L2 cohomology, you expect that to have countable fundamental group, or is it really going to be that it's inductive limit of property T things? It's like really for every cocycle or something like that.
Mhm. Yeah, for now I wanted to, I want to take something that's rigid for every possible, for every possible s-malleable deformation, right? Something like the group von Neumann algebra of SL3Q.
Right.
This is a great example that I think it's a good time to tell everybody what's going on here. SL3Z, the property T group. This is the first example that everyone studies. You start adjoining primes to it in a countable fashion, and you eventually can this builds SL3Q. And right now, it's known that this fundamental group, whatever it is, for SL3's Z, adjoin as many primes as you'd like, finitely many, that will have a countable fundamental group. So I would like to know whether or not this like limiting object can somehow has its fundamental group approximated by these generating things. It has a really nice composition. So it's definitely an example that's like what Ben is talking about. I think that's a little ambitious because you don't know enough about the structure of the fundamental groups of each of these groups yet.
Right.
So I'm going to start off by taking some kind of like cheap shot. Kifan, Sayan Das, and Krishnan Dukhan have these examples of these property T groups, which always give you trivial fundamental group, right? There's exactly one projection out there in this lattice that fits in with this group framework, and it is always the identity projection. And I want to start off by taking limits of those objects first, right? Because if I have a bit more control of the fundamental group, in this case, having it trivial at every stage of the way, I don't care which way it goes. If you have trivial, 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 suddenly countable at the limit, I'd like to know why that happens. Or if it's trivial, trivial, and then you get trivial at the very end, either way it goes. There is something interesting there.
Right.
So that's my current plan of attack.
No, yeah, it seems like a really good question. Yeah.
Yeah. But personally, I think my abilities a little too far. They're not strong enough to handle the initial question that we started with SL3Q.
But I think it's a very good motivating question.
Oh, yeah.
Yeah.
The kind of thing that you write up in an NSF proposal, maybe.
Maybe, yeah.
I have a question. This may be, I don't know if it's a good question or not, but so for groups and for von Neumann algebras, you're showing that certain objects with unbounded cocycles or non-trivial first Betti number cannot be generated by property T sub-objects, right? Even finitely many, 3, 4, whatever, probably the same argument works. Is that right?
Yeah, that's correct.
So is there a characterization perhaps of the class of groups that can be generated by property T sub-objects, or algebras, or we're not saying that they have property T themselves and that's it, or it's a larger class, right? So things that are generated by property T is somewhere between property T and everything.
Yeah, actually, I have not thought about that at all.
Am I saying something wrong, Ben? I don't know if I.
Well, David, I think so what would be your condition on intersections? Because if you don't require anything about intersections,
Right.
then...
That's right. You're right.
What should
Generally,
be
way.
diffuse?
That's right.
Yeah.
Diffuse or infinite intersection. Which.
I guess what the reason I was sort of hesitating, I mean, I can't think of anything that falls out of our work that isn't just like rephrasing things in terms of deformations. Like there's something like this that you would want some abstract characterization of like which things we can say our theorem applies to. Would basically, there's a theorem behind this which says that if you have an s-malleable deformation that is rigid on these two pieces and they have diffuse intersection and they're rigid on the join, that gets you maybe some characterization you want, but probably you want something easier to check that's not just rephrasing everything in the world in terms of.
That's right. That's what my question was, whether that's a reasonable question. Also, I will say I know Braga needs to go teach soon, so I don't want to make him squirm.
Yeah, I was about to say that before I leave. Let me just make, if David didn't know if his question was good or not, I'm gonna make one that I know that it isn't. I have a quick question. So in the corner of math that I usually hang out, there are a lot of people that look a lot at isometric group actions, but specifically on Banach spaces. And those, because of Mazur-Ulam, you split them into a linear isometric group action and a co-cycle. This is actually why I was asking about the one co-cycle, because in this literature, usually they don't write the one. But my question is more if the things you do have a more Banach spacey version of those questions in which you're not really looking at those things in L2 of G, but some more arbitrary Banach spaces, because well, that's where I come from.
I personally have not looked into this. That something that broad. Yeah, yes, of course you can talk about actions on various Banach spaces, but for me it's the sort of the co-cycles come from affine actions on L2, right? And it doesn't necessarily be L2, but the space that I like to work in is actions on some kind of Hilbert space, or even less than that, maybe like on real Hilbert spaces. Like that's about as far as I go, not necessarily.
Mm-hmm. Okay, I really need to leave right now, but I made Ben into a host, so you guys can keep on chatting. But I believe that once I leave, the recording will stop. So anyway, feel free to go crazy. Bye-bye, guys.